As we begin Unit 2, we are moving on to Section 3.1. This is some terminology about probability. We know we had a lot of terminology in the first unit, but we'll have a little bit more as we go along. Probability is a measure of the likelihood of a random phenomenon or chance behavior. Probability describes the long-term proportion with which a certain outcome will occur in situations with short-term uncertainty. So again, we talk about that's our definition of probability, and then a certain outcome is what we're talking about. In other words, what occurs is the outcome when we're doing this sort of probability experiment. And I just used the word. An experiment is a planned operation carried out under controlled conditions. In probability, an experiment is any process that can be repeated in which the results are uncertain. If the result is not predetermined, then the experiment is said to be a chance experiment. A very important law that we talk about is the law of large numbers, and this says as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of that outcome. For example, if we flip a coin, okay, we flip a coin, let's say we're talking about the probability of getting heads. Well, we've dealt with coins enough that we know the probability of getting heads would be like 50% or 0.5, or 1 out of 2. Now, if we flip a coin twice, we are not guaranteed to get heads once and tails once. That's just not how it happens because it is a chance occurrence. But as we flip a coin a whole bunch of times, the law of large numbers would say, you know, as you flip a coin 100 times, you're probably going to have pretty close to 50 heads and 50 tails. Or if you flip a coin 1,000 times, you're probably going to have pretty close to 500 heads and 500 tails. And the more and more you do that experiment, the closer and closer the observation of the outcomes will be to actually being equal to the probability. So that's what the law of large numbers says. If you know your probability is 1/2, if you do that experiment enough times, you're going to observe about half of them being whatever the outcome is you're talking about. In our case, my example is heads. The sample space, which we call S, of a probability experiment is the collection of all the possible outcomes. An event is any collection of outcomes from a probability experiment. So in our case, the sample space that I was just looking at would be the set of heads and tails. Those are the two outcomes that could occur. And when we talk about sets, we use those braces. So that would be the sample space would be that set of, it could be either heads or it could be tails. When they talk about an event, the event might be defined as, let's say we get heads twice in a row. Okay, or maybe we're going to get heads and then tails or whatever. So the event can be any collection of outcomes from that probability experiment, even if we do the experiment multiple times. An event may consist of one outcome or more than one, as we just were talking about. We denote events with one outcome, sometimes called simple events, as E sub I, many times a lowercase e. And we might have a subscript to tell us something about it. In general, events are denoted using capital letters such as capital E, and you notice that's what I used when I was looking at that event on the previous slide. Example 3.1, consider the probability experiment of rolling a single fair die. Identify the outcomes of the probability experiment and what is the sample space. So I'm going to write down our sample space. Our sample space is we could get a 1, or we could get a 2, or we could get a 3. We could get a 4, a 5, or a 6. Those are the different numbers in our sample space. And as far as outcomes, if we're rolling a single fair die and we're only rolling it one time, the outcomes would be these individual numbers. Because you could get any of those in your as you roll the die. Okay, and we would be interested in, okay, what's the probability of us getting a 4? What's the probability of us getting a 2 or something like that? So that those individual values that come up on the die, that's your outcome. The sample space lists all those possible outcomes. Basic probability. Given that all the outcomes are equally likely, and this is very important to do this formula, all the outcomes have to be equally likely. We can compute the probability of an event E using our given formula here. The probability of E, so P means probability. E is telling us we're dealing with this specific event. So probability of event E is the number of ways that event E can occur out of our sample space, and then divided by the total number of outcomes. And that's how we find our probability. So sometimes you'll see it favorable outcomes divided by total outcomes. Favorable in that case does not necessarily mean good. It's just the ways event E can occur. Let's revisit our example 3.1 with the die. What is the probability of rolling a 3? So once again, we know that our sample space was 1, 2, 3, 4, 5, and 6. And what is the probability of rolling a 3? So the probability of rolling a 3, well, there's only one way the 3 can occur. You have to get a 3. So the top number in our fraction is going to be a 1. And then the total number of values in our total number of outcomes that we have is 6. So the probability of rolling a 3 from your fair die would be 1/6. For part B, what is the probability of rolling a number larger than 4? So larger than 4 would be 5 and 6. So let me write this down in our notation. Probability of greater than 4. So I'm using the greater than symbol there. There are two ways, I'll use that color, there are two ways to get something greater than 4. The total number of outcomes is still 6. Now if we're using fractions, we would always reduce, and that would reduce to be 1/3. So that would be our probability of rolling a number larger than 4. Now again, that doesn't mean if we roll the die 3 times, we are guaranteed to get one number larger than 4. It means from our law of large numbers that if we do it a whole bunch of times, about 1/3 of the time, we will get something that is greater than 4. Part C, what is the probability of rolling an even number? So probability of rolling an even number. So our even numbers are numbers that are divisible by 2. So it divides into 2 evenly, or divided by 2 evenly. That would be 2, 4, and 6. So there are 3 of those. 3 ways that event can occur. And still 6 total events. And once again, we're going to reduce, and we would get 1/2. So our probability of rolling an even number with a fair die is 1/2. Example 3.3, lots of words on this one. Bucky has a standard deck of 52 cards and wants his friend Satchel to draw a card. So notice I've given us the picture of all the different cards in a deck, not counting the jokers. After Satchel draws a card, he puts it back in the deck. What is the probability of Satchel drawing an ace from a deck of 52 cards? Well, when we look at this, the aces are these ones that are labeled with A's if you're not familiar with cards. So those 4, let me write this out, probability of getting an ace would be 4 on the top. That's how many different ways it could occur, divided by, and if you look at the total and you counted them all up, we are already told there's 52. So 4 divided by 52 reduces to be 1/13. So that would be our probability of drawing an ace from the deck of cards. What does this say about the probability of drawing one particular type of card? Well, notice there are 4 kings, there are 4 queens, there are 4 jacks, there are 4 tens, and so on. So the probability of drawing any one of those types of cards would be 4 out of 52, which is equal to 1/13. And so that no matter which card you're trying to draw, it would have the same probability because they all have an even chance of getting chosen. Example 3-4. A survey was taken of drivers admitting to running a red light in the last year. The number of yes responses was 500 and the number of no responses was 213. Find the probability that if a person is chosen at random, he or she has run or has admitted to running a red light in the last year. So the probability of yes in this case is what we're looking for. And the number of ways that could occur is this 500. 500 people responded and admitted that they had run a red light. And then we need the total on the bottom. So if we know there were 500 yeses and there were 213 no's, we have to add those together to get the total of 713. Now, if it's something like this with really big numbers, a lot of times we will change that to a decimal number. So if we take 500 and divide by 713, 500 divided by 713, we're going to get 0.701. I'm going to round that off to 3. The rest is 2622, blah, 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 blah. So we would round that off to 0.701. We'll plan on 3 decimal places unless it tells us to do something else or the context tells us to do something else. So that would be our probability of randomly selecting a person from this survey who has admitted to running a red light in the past year. Some probability rules. We want to consider an event E, regardless of what that event is. An impossible event has a probability of 0. The way we would write that is P parentheses E equals 0. That means there are 0 ways that this event could occur. It'd be like rolling a die and getting an 8 if you only have numbers on the die from 1 to 6. That's impossible, so it'd be 0 out of 6. A certain event has a probability of 1. So if it's guaranteed to happen, that means it's certain, it's guaranteed to happen, then we would say that the probability of that event equals 1. That would be like, what would that be like? Well, let's just say rolling your die and getting a number that's less than 7. Well, since all the numbers are less than 7, you are guaranteed to get an outcome that is less than 7. The probability of any event must be between 0 and 1. So 1 is that it's guaranteed to happen, 0 is that it's impossible, but the majority of probabilities fall somewhere in between those two. So your probability of any event can't be less than 0 and also cannot be greater than 1. A complement of an event. So we are again going to consider some event E. The complement is our term that we're talking about here. The complement of event E is when event E does not occur. We use this symbol E with a bar over it to represent the complement of E. The probability of the complement is given by this. The probability of the complement, notice the bar over there, the probability of the complement of E is equal to 1 minus the probability of E. Now, hopefully that makes sense because 1 is where you've got everything. You're subtracting out the ones where E occurs, and that leaves you with the ones where E does not occur, and that was our definition of a complement. So the formula is that P of the complement of E is 1 minus the probability of E occurring. Notice also, if you rearrange that formula a little bit using algebra, that the probability of E is also equal to 1 minus the probability of the complement of E. So there's nothing magical there. It's just algebraic rearranging of that formula, and those things are both true. Going back to example 3.3, we're looking at example 3.5 now. But our deck of cards from 3.3, you'll have to go back in your notes and look at that. I've got the picture here on the slide. But what is the probability for Satchel not to draw a queen? Well, if we think about that not word, we're talking about the complement. So we're talking about the probability of not getting a queen. Well, that means it would be 1 minus the probability of getting a queen. That's our formula for a complement. So if we look at the queens, remember we have 4 queens. So it would be 1 minus 4 over 52, which is 48 over, well, actually, let's reduce. We know that 4 over 52 reduced, because we did that one earlier, to 1 over 13. And if we subtract that, we get 12 over 13. So that would be the probability of not getting a queen if Satchel is choosing a card. 2 events are disjoint. That's a great word. But here's the term. Here's what it means. Disjoint if they have no outcomes in common. So our complements have to be disjoint. Otherwise, our formulas wouldn't make sense. Another name for disjoint events is that they are called mutually exclusive events. Okay, disjoint or mutually exclusive means that the outcomes are completely separated. There's no overlap. They have none in common. The probability of either of two disjoint events occurring. So if we consider these 2 disjoint events, and we'll call them A and B, the probability of either A or B occurring is, so probability of A or B occurring, that's our event right here, is just going to be the probability of A occurring plus the probability of B occurring. So you just take those individual probabilities and add them together. Back to example 3.3. Bucky has his standard deck of 52 cards. Wants his friend Satchel to draw a card. After Satchel draws a card, he puts it back into the deck. Find the probability for Satchel drawing a queen. Well, we just actually did that a couple examples ago. The probability of drawing a queen, since there were 4 queens, was 4 out of the total of 52, which reduced to be 1 over 13. So that is our answer for part A. And I'm going to leave that up here because I think we're going to come back to it. But for part B, the probability of drawing a spade. Well, a spade, if you're looking at a deck of cards, again, if you're not familiar with cards that much, these up here at the top are spades. We have spades, look like little pointy things. These are clubs. These are hearts. And these are diamonds. But this top one, these are the spades. So if you look at that group, we have 13 total spades out of a total of still 52 cards. If we reduce that, we will get 1. Let me erase my clubs here. You'll have to just remember that, I guess. But 1 over 4 is our number of spades, or our probability of selecting a spade from our deck of cards. Now, find the probability for Satchel drawing a spade or a heart. Okay, so probability of spade or heart. Now, this is an or statement, and the spades are all right here, and the hearts are all down here. So these are disjoint events. So that means we can take the probability of a spade plus the probability of a heart, and we can just add them together. And we already did the probability of a spade. It's 1 out of 4. And if you think about the probability of a heart, pretty clearly there's the same amount of hearts as there are spades. So the probability of drawing a heart will also be 1/4. We add them together and we get 2/4, which is 1/2. So our probability of drawing a spade or a heart would be 1/2. And again, that pretty much makes sense if you're looking at the picture, because you've circled 2 of those rows and 2 of the rows are not circled. So half of them are in our favorable outcomes, or our event that we are considering. Consider 2 events, again, event A and event B. If the probability of event B occurring is the same whether or not event A occurs, then events A and B are called independent events. They are not dependent on each other. They are independent. Things like flipping a coin and rolling a die. The outcome of the coin does not affect the outcome of rolling the die. Example 3.7. When Satchel draws a card, he puts it back into the deck before drawing another card. What if Satchel draws a card, which is a spade, and does not put the card back into the deck? Let's say that Satchel then draws a heart. If Satchel had replaced the spade before drawing a heart, how would this probability be different from when he did not replace the spade? Okay, so this leads us into a word called, or a phrase called with replacement. And we also have without replacement. So we already did the chances of, well, actually, let's see. What if Satchel draws a card, which is a spade, and does not put the card back into the deck? That's without replacement. That's the second one. So let's take a look here. Let's do the first one first, because I think this one should make sense. Probability of him drawing a heart, given that the card he picked out the first time was replaced. So we know that's 13 out of 52, because we just did that on the previous slide, which is 1/4. So that's the chances of him drawing a heart after Satchel drew a spade and put it back. Now, what happens if he does not put it back? And unfortunately, I don't have my slide here to look at. But notice the number of hearts is still 13, right? Because the card that Satchel drew out was a spade. But what changes is there are no longer 52 cards in our deck because Satchel took one out. And he took one out, and so therefore there's only 51 cards left in the deck. And so that changes our probability. The probabilities are not the same. So if you take out a card and don't replace it, you are having two events then that are dependent. If you replace the card each time, then those events and those probabilities are independent. So how would the probability be different? Well, actually, if you've taken out a heart and if you've taken out a spade and you're going to draw a heart without replacing the spade, you actually have a slightly better chance of choosing a heart the second time than you would if you did put the spade back in. All these spades and hearts are getting me confused, but with replacement, the events are independent. Without replacement, the events are dependent because the probability is changing. It's affected by the previous outcome. Example 3.8. Consider the event that it will rain tomorrow in Houston, Texas, and also the event that it will rain tomorrow in Galveston, Texas, a city that is near Houston. Are these two independent events? So independent means the outcome of one does not affect the other. I would say that these are probably dependent events because the rain in Houston will affect, well, let me say it this way. If it rains in Houston, it is more likely to rain in Galveston because they are near each other. Okay. Now, if you were talking about it raining in Houston and raining in Springfield, Missouri, that's probably going to be independent because those two things are not affecting each other. They're not close enough for that to matter. But when those two places are close to each other, the rain in one place, if it rains in one place, it's probably more likely to rain in that other place because they're close. It'd be like saying, if it rains in Monette, is it likely that it's going to rain in Mount Vernon? And yeah, probably because they're close to each other. The probability of two independent events. If events A and B are independent events, then the probability of both A and B occurring, so probability of A and B, is the probability of A times the probability of B. So this is the chance that both of them occur. That's where P of A is the probability of event A occurring, and P of B is the probability of event B occurring. So you multiply those two independent probabilities together. Example 3.9. What is the probability of Satchel drawing a heart, replacing the card, and then drawing a spade? So probability of heart and spade. Now, remember we did one earlier that was an OR problem. That's different than this. So the chances that Satchel draws a heart, remember, is this row right here. That would be 13 out of 52. Well, actually, let's go back before we even get to that. These two events, because we are replacing the card, these two events are independent. So that means we're going to be able to take the probability of getting a heart times the probability of getting a spade. And we just talked about this in a previous one. The probability of getting a heart is going to be 13 out of 52, which is 1/4. The probability of getting a spade is the same thing. We multiply that together. 1/4 times 1/4 is 1/16. And so that is our probability of getting a heart on the first pick and a spade on the second pick. Example 3.10. Given below is a table for a group of adults, which is divided into gender and the hand that they write with. So we've got our table that has male, female total, and right-handed, left-handed total. Part A, find the probability that a randomly selected individual will be a male and left-handed. Now, these are not independent events because the first outcome, them being male, affects the outcome of them being left-handed because they're different between males and females. So what we have to do this time is we have to view this a little bit differently. So we want probability of male and left-handed. And when we have a table like this, we can actually do it fairly easily because we can just look at, well, where are the males that are left-handed? It's these 12. Those are the 12 ways that outcome could occur. And so 12 goes on the top of our fraction. And then we look at the total, which is 100. So it'd be 12 out of 100. This one, maybe a decimal would be nice because it divides out nicely, but 0.12 would be our probability of choosing a male who is also left-handed. Okay? For part B, find the probability that a randomly selected individual will be a male or a female. All right, well, these two groups are what we call, remember, disjoint. So the probability of selecting a male or a female would be the probability of selecting a male plus the probability of selecting a female. And in this case, that's going to be the total number of males is 50 out of 100 plus the total number of females is 50 out of 100, which gives us 100 out of 100, which is 1. And that probably was obvious before I even started doing the math, but obviously if the only two groupings of the gender are male and female, you're going to get one or the other every time. So you are certain to get a male or a female if you select somebody from this group in this table. For part C, find the probability that a randomly selected individual will be a woman given that she is right-handed. Now this leads us into a little bit of a different case. It's what we call conditional probability. The way you actually write this is the probability of being a woman, wow, I can spell, woman, given that they are right-handed. And what this means is our total sample space has changed. We are only considering people who are right-handed. Let's see, make sure. Yeah, we are only considering people who are right-handed. And now from that group, what are the chances of getting randomly selecting a female? Well, 42 is the number of females in that group out of the total of 80. So again, we could reduce this. That'd be 21 over 40. Or if you wanted to change it to a decimal, you could, just 21 divided by 40. but that would be our probability of selecting an individual who is a woman, given that that person is right-handed. Another important kind of phrase that we have to look for is, aside from the complement, is this phrase of at least one. The probability of at least one occurring is 1 minus the probability of none occurring. Okay, so if you've got your options, you could have 0 occurrences or 1 occurrence or 2 occurrences or 3 occurrences or 4 or so on. The probability of at least one is all of these. That means it's all of them minus the probability that none occur. And so that's why this formula works the way it does. And this is going to make our math a lot easier, because instead of combining all of those different options for occurrences, we just subtract out the 0. So example 311, according to Master Foods, the company that manufactures M&Ms, 12% of peanut M&Ms are brown, 15% are yellow, 12% are red, 23% are blue, 23% are orange, and 15% are green. If you randomly select 3 peanut M&Ms, compute the probability that at least one of them is green. So the probability of at least one green. Well, there's that phrase that we're trying to look at. This is going to be 1 minus the probability of 0 greens. Okay, so let's figure out our probability. The probability of not green, or actually let's use our complement notation. The probability of green not occurring would be all the others, right? So it's 1 minus the probability of green, which is, where is it here? 15%, that's 0.15 as a decimal. You do have to change them to decimals. So 0.85. That's the probability that it's not green. Now, the probability that all 3 are not green gets a little bit trickier. So what we have to do for probability of 0 green, since we're choosing 3 times, is we have to take that 0.85 the first time times 0.85 the second time times 0.85 the third time. So this would be not green, not green, not green, and we multiply those together. The reason these are independent events, even though we're selecting M&Ms and it doesn't say that we're putting them back, is because there's so many M&Ms in the world that when you talk about these percentages, that choosing one out doesn't change your percentage at all. Or so tinily it doesn't, such a small amount it doesn't matter. So 0.85 times 0.85 times 0.85, and that gives us and I'll put it right down here, 0.614125, and then we're going to subtract that from 1, and we're going to get 0.385875, and if we round that off again to 3 decimal places, 386 would be our probability that at least one of them does end up being green, at least one of the 3 selections. So we had to go through several pieces there, but that's how that one works out. That is the end of section 3.1, and again, go ahead and get after those problems. And again, the sooner the better. And if you have questions, please don't hesitate to give me send me a message and ask about it.